These are the notes on thermochemistry, so this will be the notes on slides 1 through 25 for our thermochemistry unit. So when we study thermochemistry, we're going to study the driving force, we're going to study enthalpy, entropy. We'll do a lab on Hess's law and learn Hess's law. We'll learn about Gibbs free energy, and then we'll also learn about the rates of reactions. So when we study thermochemistry, we know that thermochemistry is the study of changes in the heat energy that accompany the chemical and physical changes. And then just a reminder that that delta, that triangle there, means delta. If I say delta, that's what I mean, and that means change. So anytime you see delta, most of the time you've seen it in a delta T situation, so the change in temperature. So we'll use that again for this unit. So temperature is the measure of the average kinetic energy of the particles in a sample of matter. This should be review from the solutions unit and the liquids and solids unit, where we talked about energy in those as well. Joule is the SI unit for heat energy, so we'll come back to the specific heat equation and talk about measuring things with joules. And then heat energy is the sum total of the kinetic energies of the particles in the sample of matter. So those are just some review definitions that we have here. So temperature, again, is the average kinetic energy in the sample of the particles in a sample of matter. So the greater kinetic energy, what would happen is that because the kinetic energy is getting greater, those molecules are going to move faster, and thus it would feel hotter. And that should be a really good review of the information from the liquids and solids and solutions unit. So hopefully we're all feeling comfortable with that. So if something, and also the gas law unit, because we know as the kinetic energy increases, particles are also going to move faster. We know that heat always flows from matter at high temperature to matter at low temperature. So this will be very important when we're talking about thermochemistry. And when we can apply that to a real world situation. When we open the door in the winter, cold does not come in, the heat actually will leave. So when your parents yell at you for leaving the door open and saying you're letting all the cold air in, you can actually say, well, based on thermochemistry, heat actually will be leaving the house instead of cold air flowing in. So heat energy is the sum total of the kinetic energies in the particles of sample of matter. So we know that heat flows from hot to cold. And so we've got an example set up here, and this is actually the same slide almost as when we studied specific heat and studied calorimeters. Not colorimeters that we used in Beer's law, but calorimeters, where we heated up a metal and put it in really cold water, and we were able to take the temperature change of the metal and of the water, set them equal to energy in is equal to energy out, and be able to calculate the specific heat of unknown metals. So that leads us to the actual specific heat equation and definition. So remember, specific heat is the amount of heat energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. So joules per gram degree Celsius. And then this is our algebraic equation, and then I will expect to see it in your T-chart equation here as you set it up, mainly so that you can continue to understand how to cross out those units. So joules per gram degree Celsius is your specific heat right there. Remember, this is our energy, which is measured in joules. We'll take the mass of the substance, and then there's your delta, and we'll take the delta T of the substance. So when we heated water, we used 4.184 joules per gram degree Celsius, and as you remember from first semester in the lab practical, each substance has its own value. Here's just a slide that shows you algebraically how to split up the specific heat equation to solve for the different variables. So you don't necessarily need to memorize this slide, it's just showing you exactly how we can solve for each of those different things. So if we have a sample problem here, a 4-gram sample of glass was heated from 274 Kelvin to 314 Kelvin, and this absorbed 32 joules of heat. What's the specific heat of the glass? So I'm going to first start with writing my algebraic equation down, so Q equals mass times Cp times change in temperature. And then I'm going to write in the values that I know. So I know that my mass is 4 grams. I know that I'm solving for the specific heat. Over here I'm going to solve, I need to calculate my actual change in temperature. So I'm going to solve for that. And then I'm going to set it equal to, and I know I set it equal to joules, and I'm actually given that right there. So go ahead and pause the video so that you can calculate the specific heat. So hopefully you pause the video and we're able to calculate the specific heat. Once you get that, you should get 0.2 joules per gram degree Celsius. Here's another sample problem. So now we know the specific heat is 0.2. We're going to calculate how much heat will this glass sample gain when it's heated from 314 to 344. So we're going to set up our equation again. So we know we have a 4-gram sample. and we know our specific heat is 0.2 joules per gram degree Celsius. We need to calculate the temperature change, which is equal to 30 degrees Celsius. And so now pause the video again and go ahead and calculate for your joules. Hopefully you paused the video and calculated that your joules were 24 joules to heat that glass up. Another problem here, so go ahead and pause the video and then try this setup and then I'll walk you through it. So hopefully you paused the video and were able to calculate this. So the problem says determine the specific heat of a material if a 35 gram sample absorbed 48 joules as it was heated from 293 to 313. So you set up your Q equals mass times Cp times change in temperature. So you know that you have a 35 gram sample. You know you're solving for the specific heat because it asks you that in the question. Over to the side, I'm going to calculate my temperature change. So I know that my temperature change was 20 degrees Celsius, and I'm going to set that all equal to 48 joules. So then I'm able to calculate my specific heat as 0.0069 joules per gram Kelvin. Now, we don't necessarily need to change that degree Celsius to Kelvin, because if I raise 1 degree Celsius, I will also raise 1 degree Kelvin. So all we're using that temperature change value for is just a temperature change value, not necessarily needing it to be in degrees Celsius or in degree Kelvin. So we don't necessarily need to convert there. So a new problem here. So on this one, I'll walk you through it together. Biggest thing on this one is that we need to watch our units. And so we need to change that 980 kilojoules into your joules because our Q equals mass times Cp times change in temperature must be in joules so that we can calculate specific heat. We need to change our liters to milliliters and our milliliters to grams because we know that 1 mil equals 1 gram. So we've got to change those mils to liters, and then we can just equal that to grams. And then our Kelvin, like I said before, we don't need to change to degrees Celsius because if I increase by 1 degree Celsius, it's the same as increasing by 1 Kelvin. So now as I set up my problem here, I can plug in my variables. So I know I have 6,200 grams. I'm calculating with water, so I know my specific heat is 4.184 joules per gram degree Celsius. I'm trying to calculate the temperature change so that then I can find, so my temperature change in this case would be 37.77. Then I can find the final temperature because I know the initial temperature. So I can set it up using that equation right there and calculate for my final temperature. You can also just set up this T final minus 291 in that algebraic equation and just solve all right away for that T final if you'd like, if that makes sense to you. So enthalpy is the heat content of a system at constant pressure. So the heat of the reaction, so that's your change in H of the Rxn is reaction, is the quantity of heat released or absorbed during a chemical reaction. So we know that the change in H of the reaction is equal to the change in H of products minus the change in H of the reactant. So this is the equation that we will use and become very familiar with in our thermochemistry unit. Only changes in H can be measured. So if we make water, is energy released or absorbed when we look at this equation? So if we're just looking at that equation, we don't know if energy was released or absorbed because we don't have an actual joule value. And so a thermochemical equation will actually include the value either released or absorbed. And so in this equation, we've got the heat released during the reaction because it's a product. So because it's showing it on the right side, it's energy released in the reaction. So again, because the value is a product, we consider it energy released because it's being produced. So energy released means that this is exothermic. So exothermic again means released or absorbed. Or released, not absorbed. If I have 4 moles of water instead of 2, all I would need to do to that kilojoules is double it because I have twice as many chemicals. So it would just be 967.2 kilojoules. If I cut it in half, it would just be 241.8 kilojoules. So hopefully that's making sense, and those are relative values based on the amount present. So if I reverse the equation, because the forward equation is exothermic, my reverse equation would be endothermic. So the reverse reaction is endothermic. It would take energy for that to happen. So when we talk about enthalpy change or energy change, when we have an exothermic reaction, we know that we have, if I were to write that value by itself, I know that I have a negative number. So in this equation right here, I'm not including the value within the chemical formula. I'm including just the value of the change of H. Because it's an exothermic, I have to include a negative number. Hopefully that's pretty straightforward from when we did liquids and solids and solutions. So that negative number is telling me I have an exothermic reaction. And so we need that to show it's exothermic. Our energy graph here just can show that we've got our reactants at a higher energy level than our products, and this is just showing heat released, and that's showing just, potential energy, ball rolling down the hill, reactants and products. So the products are more stable because they're existing at a lower energy level. So whichever reactants or products is existing at that lower energy level is the one that's going to be more stable. And they're favored because they're at a lower energy level. So we would say that they're favored as well as more stable. So again, if we reverse the reaction, we have an endothermic reaction, and that would be it takes energy. So here's this thermochemical equation showing that joules in the reactant side now, not in the products, and so it's showing that it takes energy for that reaction to happen. So again, that's showing that that takes energy, and that's an endothermic reaction. And so in an endothermic reaction, as it's showing, it takes energy to happen. So here my reactants are existing at a lower energy level, so we would say that they are favored in the equation. So whatever, again, is existing at that lower energy level is favored. And this is just an energy diagram showing heat was added, showing energy is being absorbed for this reaction. So an endothermic reaction requires a positive sign, so again, because that's written outside of the chemical formula, this would need a positive sign to show that this is an endothermic reaction. So when it's not included in the chemical formula, we do need to make sure that we include those plus and minus signs. Alright, you should be able to answer all of your questions on the More Thermochemistry sheet and check that at the end of class. If you don't get done, you can check it on Monday.